Hi, I'm Skylar, and we're going to do another bomb lab question. In this case, we're looking at a, a jump table. So let's get into it. And this might appear on your midterm, depending what the professor says. So, first things first, we're going to look at our main function. And we see this. It's calcul, a TOEI. A TOEI is, it's basically like a string to an integer. Okay, in this case, the A refers to ASCII to integer. Okay, and we know calls that are at PLT, anything, right? We'll place that value into REX. Any call that the return value will be into REX, and we can just assume that our inputs, that we put in, will be converted into an integer because that's I, and be put into REX. Okay, let's draw our stack. Okay, I always do this for all bomb lab questions, and it's to draw the stack because I think it's very helpful. So there's two things for bomb lab questions. You want to always draw the stack, and you want to keep track of registers, and also you want to know your fundamentals. This is the third video of the two that I already made, so I recommend checking out those two other videos. Also, important notes, I think I forgot to mention this in the last video for the string question. I'll just read this. But basically, fundamentals is, remember, look at REX for what the value returned from a calcu is, and make early assumptions and dive deep to confirm those assumptions. Yeah, so just read this, and you should understand if you actually watched this video before. So bomb lab, what helps you a lot is making assumptions and having strong fundamentals. So what are some more fundamentals? It's knowing stuff like this. What exactly call Q does, what exactly push does, what exactly pop Q does, what exactly leave Q does. And being able to trace each instruction on the stack is a very important skill. The last two questions should give you fundamentals with this. Okay, but now we're looking at a different fundamental concept, which is switch statements. Okay, so what I like to do is, starting from here, I will actually, so I'm actually going to start from here. So in this case, let's just start with the stack being at 0. Say RSP is here. Okay. In this case, we're going to move REX to some value that's with respect to our BP. Okay, actually, what I'll do instead is draw RSP like right here somewhere. And I know I kind of cut it out, but knowing where RBP is not important. What's more important is having the fundamentals from the previous question to know what RBP actually is. In this case, RBP is the frame pointer right here. So as the stack pointer is like pointing somewhere down here, the frame pointer is pointing somewhere up here. Okay, so that means when we subtract something from the RBP, we're placing our local variable somewhere in here, which makes sense according to this diagram. Okay, so let's just assume RBP is here. In this case, this would be our old RBP value. In this case, since it's the main function, I don't think there is an old RBP value, but that's just the general case. I could be wrong about that, but that's not really important. The important part is your RSP is right here. Your RBP is somewhere above it. Okay, so let's just draw. We're moving REX into negative 12 of RBP. Okay, why I say 12? Okay, I always like to draw the stack like this. So I use base 10. So that means negative 12 will be somewhere here. Okay, this makes sense. Do you know why? Because we're moving at negative 12, which means that this thing will be taking up 4 bytes, which makes sense because it's an integer. So I'll just say inputs. Be placed there. Okay. You can do this. We're going to share this bomb lab, so you can draw a more accurate stack based on the previous code, but I'm not going to show it here. because I don't think it's that important. But what's more important is just knowing the fundamentals. Okay, so so far we've executed these two instructions. Now what we need to do is move this value into REX. Okay, so this looks kind of dumb, right? But a lot of times what you have to understand is the BOM lab, or specifically the compiler, with low optimization levels, tends to do these like seemingly not really important instructions, and just accept that. Yeah, so we're gonna move this value right here that we place in here as well, which is an REX, into RDI. And what do we know? Another important BOM lab concept is what registers correspond to arguments. So RDI is actually the first argument. So now we know that magic takes in one parameter and it will be RDI. Why not 2 parameters? Why not 3 parameters? Well, we're just going to make that assumption because we don't see any RSI, which would be the second parameter. Okay? So based on that, we're going to call this with the parameter of our input, right? And then we're going to compare the return value of magic with 0x16, which is 22. You can do the math yourself, or I can do it for you. Let me do the math for you. 0x16, what I like to do is for this first digit, I do 16 to the 0 and 16 to the 1. Okay? And this would be 16 plus 6, which is equal to 22. I'm going to make an assumption that you know how to do hex to base 10 calculations, but if not, you can watch a YouTube video online. Okay, so now that we have that, we compare that return value with 16, and then we have a jump equals if it is, sorry, not 16, 22. See, even I messed that up. It jumps to E4, okay? Now the important part is that it jumps beyond this explode, which is what we want. So that means we need to input a value so that the return from magic, this magic function, is 22. So we can explode, we could avoid this explode, okay? Okay, so now that we understand that, now let's actually keep tracing our stack and tracing our registers. So RSP is here. Okay, let's do this first line. We're gonna call Q to magic. Okay, remember, what does call Q do? These are the two fundamentals. Number one, it places this thing into RIP, which is the program counter, which tells the program which instruction to execute next, and it pushes this onto the stack, the return address. So in this case, the next instruction, the address of the next instruction. Okay, when I say push, I'm saying it's like an actual push. So what does push do? Well, push increments RSP by 8, and then places the return address onto that stack at that specific RSP location. So let's just say, so yeah, so in this case it would be 4013D5. And you might be wondering, why was RSP here in the first place? I chose that arbitrarily, and that might be wrong based on the actual code, but remember, the important part is like the concept fundamentally. You would have to inspect the main function to see what are the actual relative addressings of these registers. Okay, so now that we have that, we're finally at this part of the execution. Why? Because we just placed this into REP, which means we're executing this next. Okay, fundamentals. What does push REP do? Okay, so right now REP is right now let me quickly see what is REP. Yeah, so REP is like something right here. Pointing right here. So we're gonna save that. And this is just convention of what we call these saved registers. Yeah, so we're gonna push REP. Let's say REP, which is equal to -8. If you want to know more about these fundamentals, I suggest watching the first video where I tracked through a certain recursive function. I won't tell you which one that is, but yes, I think it's a really good video for understanding the fundamentals of the stack and these REP values and what they all mean. Okay, so now we're at -40. Our RSP is also decremented because that's how pushing onto the stack works. Okay. Okay, so now we're gonna move RSP into RVP. Okay, so that means RVP is now 4. You'll always see these two things. Whenever you're in a function, you'll always see these two instructions. And brush up your fundamentals for that from the last video. Okay, now we're gonna move RDI, which is the same as our inputs, if you remember, into negative x 0x14 RVP. Okay. So remember, RVP is now at negative 40. Let's write that. And negative 14 would look something like this. Okay. So negative 14 would be equivalent to 16 plus 4, which is equal to 20. So this is 20 down. Okay, so it would be here at negative 60. Okay? In this case, what we're putting is, let me see it one more time. Yeah, it's our RDI value. So RDI, I'm gonna say equals input. Okay. Now we are done with this so far. So now we're gonna do this. We're gonna move 12 into negative 4 RVP. Okay, so negative 4 RVP. Where is that? That would be right here, right? And this we're missing. We're putting in 12. Okay, so oftentimes when you see things being placed in to the stack, like relative to some RVP value, specifically negative RVP value, because obviously we had to. This is like from your fundamentals if you watched the previous video. So where we put our local variables. Okay, yeah, I just spoiled the answer. That's where we put our local variables. So we're basically putting local variables onto the stack. Okay, in this case we're putting 12. So that means there's like some variable that we assign to 12, like in this function. Okay, so we're just gonna put 12 here, just straight up, because that's exactly what's being done. This would correspond to an actual variable holding the number 12. I want to make that very clear. Okay. Now we subtract 7 from REX. Okay. Now when you see these instructions, first of all, jump above, and then even more importantly, something that looks like this. You should automatically think jump table. What is a jump table? Okay, I'll brush up on your fundamentals. Okay, so a jump table is basically you do something like this. This is the start of your jump table right here. And this is how you index into your jump table. Use the REX value. Because it's REX times 8, right? Which means if it's 1 times 0 times 8, then obviously I'm looking at the first entry in my table. If it's 1 times 8, I'm looking at the second entry. And why 8? Well, because the jump table stores addresses that we jump to, right? And we're putting that into REX and then jumping to the actual address itself, right? So REX would hold like a specific address, and now we're gonna jump to that specific address using the star right here. Okay, it's a very important detail. Okay, so now this thing right here gives you a hint on the ranges of this switch statement, right? So for example, let's say let's just like test. What if it was like REX, or in this case the input looks something like 1, for example. Then we do subtract from -7, so we get -6. Then we compare -6 with 7, and we jump above. Okay, is -6 above 7? And you might think, yeah, it's greater than 7, right? But that's JG. That means greater. Jump above is unsigned comparison, and we all know that negative numbers, right? If they're interpreted as unsigned, that means they always have a 1 in their most significant bits. So that means jump above and unsigned, that means this is going to be greater. Or, sorry, I shouldn't say greater, I should say above. Now, here's more fundamentals. The jump above, if it's ever resolves, that's the default case statement, okay? That's really important detail. If jump above resolves, which means that my inputs is above, right? Which means it could be less than, technically less than, but above, okay? If it's above. So how do you check if it's above? You look at the actual binary and you compare most significant bit to least significant bit and see which one has like the 1 and the other one doesn't have a 1 or like a 0. Okay, which one's above? Unsigned comparison, okay? If it resolves, that's going to be a default case in your switch statement. Very important. Okay, and that means it jumps to 401A0. Sorry, 4012A0. I cannot read. Okay. 4012A0. So let me just draw that line, which is right here. Okay? Yeah. And okay, so that's what we know. Okay, so it's really important. I wrote it right here. Okay, first I wrote like what a jump table actually is. And then I wrote so in the second notes. So yeah, it's very important to know the range and what are the gaps. And I'll explain more about what I mean by gaps. But first, let's determine what are the range of the valid case statements that will not resolve to the defaults. Okay, and we can see that. Basically, here's a trick. You want to assume you start at 0 because the compiler will always do that. Your compiler will start at 0 relative to this relative to this 7. Okay, so what does that actually mean? Well, what if our input is 7, right? That means 7 minus 7 equals 0, right? Is 0 above 7? No, it's not. And these are how switch statements always work in assembly, right? So actually a quick tip is actually the smallest number will actually just be whatever value is here. But you shouldn't always think about it like that. You should think about it conceptually and like plug in actual values, right? So that means we have potentially 7, 8, 9, 10, 11, 12, 13, 14. Okay, why do I say all these values are valid? Okay, let's see. So 7 we saw, we subtract 7 from 7, so we get 0. 0 is not above 7, right? Because we're comparing like this. Okay, now 8 minus 7 is 1, not above 7. So you can kind of like make your own formula. I'm not going to make one for you because you should learn how to make your formula based on like these. This is like a common pattern that you'll always see. Okay, and if we go all the way to 14, okay, 7, which equals 7. 7 is not above 7. So that's the last one. But once you get to 15, that means 15 minus 7 is 8. 8 is above 7, so that means it's a default case statement. So that means the valid cases are these. Okay, but that's a little hasty. I wouldn't say all of these are valid. Why do I say that? Okay, let's go to the jump table. So first of all, let me review your fundamentals of the jump table, right? So we take that input, this one, we subtract 7 from it, so we get like the smallest number starts at 0, right? We compare it with 7. Okay, if it's above, we jump. Okay, and then we move this value, which basically does nothing, and then here is always the start of the jump table, which I put conveniently right here. And the jump table, like I said, we index into specific entries, which are addresses that we actually go to execute the actual logic of our specific switch statement. Okay? So yeah. So that means if it's a 0, right? That means it's 0 here. 0 times 8 plus this, right? We're going to put that into REX. Right? Remember, this is a move though. So we're going into memory here. So that means we're not looking at this anymore. We're looking at the memory. So we're looking at this. And we're placing this into REX. This is also addressed though, which is why when we jump, we don't we jump specifically to like the de-address version of REX. Right? So that means we're de-addressing this, jumping to it. 401275, which is right here. Okay, I hope that makes sense so far. I'll give you time to think about it, what I just did. So that means this corresponds to the address of the instructions I just start executing for the case equals 0. And then you can kind of think about it linearly, okay? This is for case equals 1. This is for case equals 2. Case equals 3. Okay, when I say case equals 0, 1, 2, 3, I obviously mean 7, 8, 9, right? But I'm just saying that for convenience. So this is 7. I'll write it right here. 7, 8, 9, 10, 11, 12, 13, 14. Okay, now I mentioned gaps. Now what do we know about, what does that even mean? Okay, so remember the default case statement would jump all the way here, right? Well, we don't actually want that. Or sorry, a lot of times we have gaps in our jump table. So for example, let's say case 7 was there, and case 8 was not there, and case 9 was there. And that's exactly what we have here. Case 8 is actually the same address as our default. Boom. And we can look at other ones. That means no case 11 is here either. Okay? Makes sense? Okay, sounds good. Okay. Now that we know, that means we need to choose the right case statement, which will inform our input. So that means our input should be one of these numbers. Probably not the default case, but we can check that out. The default case moves this into RBP, which is right here. Or sorry, -4 RBP. It's a really big number. And then puts into REX, right? And then does this logic. So that means magic will return some very large number. Which is probably not 22. Or I'll just tell you it's not 22. So it must be something, we must have to go to a different statement. Okay, let's try 7. What if we go to 7? 7 is this. Okay. That means we should go here. Right? If we go to 7, we're moving 0 into here. So this becomes 0. Okay, let's keep looking. Then we jump to let's see, A7. Where is A7? Right here. Okay, so it looks like this is basically a break. Every time you jump to the end, that means you're encountering a break. Because then you place that value into REX and then you're done, right? Okay, but that doesn't seem right, because that just means like we're putting 0, but we need 22, right? So it can't be that either. So it cannot be 7, and it cannot be a default base case, right? So we can cut those out. We know 8 is a default, and 11 is a default, and we know everything else is a default. Okay, so now it's between 9, 10, 12, 13, 14. What if we choose 9? If we choose 9, that means we're here. We're at 40127E, which is this instruction right here. Looks like we're moving 1 here, so 1 is here instead. Okay. So we move 1 into here, and then we add 1 to it. Okay, so now we have 2. And then we shift it left by, or what does this do? SHLL. So I'm pretty sure, yeah, this will multiply to itself 2 times. Okay. But let's just make sure it does that. SHLL. SHLL. Negative 0x 4% RBP. Yeah. So I'm low-key, my fundamentals are kind of bad. Yeah, so SHLL means that we're shifting left, right? And when you left shift, it multiplies the number by 2. But you might be thinking there's no count specified. And that's actually what I got confused by. And when that happens, and don't worry because I even forgot, but when there's no count specified, its default is 2. So that means we're going to multiply the 2 to it. So now we have 2 and we have times 2. So now our value here is 4. Okay? So let me repeat again. When you see this, no argument, no second thing, then we're basically doing that value times equal to 2. Okay. Yeah. Okay, so secondly, we're then going to jump to A7. And now we know that we're done. But that's 4, so that cannot be correct. So now we know 9 is not correct. So now we look at 10. What is 10? 10 is this value right here, which is right here. Okay, so it looks like we're not going to move 1 here. We're going to add it. And what this looks like to me is it looks like we have a case statement, but that does not have a break. Specifically at 9, we don't have a break after the 9. So we just go straight to the case 10. Okay? Because we're going to the same code that we already used. So we're adding 1 to here. Remember, our original value is 12. So that means we're going to add 1 to it. Oh my goodness. Wait a minute. I hope I did not confuse a lot of people. But why did I say 12? That makes 0 sense. A is 10. Okay, let me change that. I hope I did not confuse a lot of you. Or maybe you guys are banging your head against the wall. Okay, but this is actually 10. Right? A is 10. Okay, now we're adding 1 to it. So now, right here, it becomes 11. Okay. That's good. Looking good. 11. Okay, maybe. Now we have foresight, right? 11 times 2. Oh, isn't that 22? Okay, let's see. So now we, as we said, this is going to multiply. Yeah. So now this becomes 22. And now we go. So it seems like the answer is 10. And we don't have to verify the other ones. Or we can. On the test, I would suggest you verify the other ones to make sure that they don't return 22. Or else that means there's multiple correct answers. So in this case, we have to put 10. I hope that makes sense. Hope I didn't really confuse you guys, especially with that 10. I know I can get confused with the hex to base 10 conversion, but other than that, that's pretty much most of the fundamentals that you need. Make sure to watch the other 3 videos. Also, I'm also down for feedback, so include that. And yeah. Let me quickly review everything that we covered in these last 3 videos. So obviously we have switch statements. Some very important concepts is the following. Right? We have gaps. Right? Very important to note that gaps are basically like things like 8 and 11, which go to your default case. This is stuff where you see case 7, right? And then case 9. So we skip 8. So that means 8 is a default, right? Know this pattern right here. To subtract, compare, and then jump above. That will inform you what the range of values can be for the switch statement. Of course, there's gaps. Okay? Then try each one until you finally get your right answer. It's very important to know this pattern. Remember the jump table, which is when you see something, this is like shouting jump table, right? This is the start of it. Specific REX is like your input, and or basically your modified input because you subtracted from it, and it's 7 corresponds to this one, 8 corresponds to this one, and so on. Okay. So once we have that RX value, we should jump to it. So we should deaddress that and go to it, right? So we should go to that instruction. So, just to make this more clear, you might be a little confused. Like, what happens if we don't have a star here? And without the star, it would try to jump to the value in REX directly rather than using it as a pointer to the destination address. So the star basically means we're dereferencing. We're using the value in REX as a memory address to jump to. Okay? I hope that makes sense. Okay. So yeah, that's reviewing the question we just did. Now the string question. More very important things is, remember, strings are 0 byte terminated or null byte terminated, which is represented with zero. So that means if we see something like this and we're given like an assembly dump, these are all the hex values of actual characters, right? So each thing is a character. A character is 1 byte, and 2 hex digits is 1 byte, right? Because each hex is 4 bits. So that means this entire thing is one string, which starts from here. Because remember, a string is a character array, and character arrays are contiguous in memory, starting at the lower address, going to the higher address, right? Okay. You might be thinking, okay, what if it was big endian? Would it be the opposite? Oh, no. It would actually be the exact same. Because endianness refers to like within the byte ordering within the data type. And these are all 1 bytes because they're all characters. And arrays are always contiguous in memory from lower address to higher address. Okay? So hope that's not really I hope that's not confusing, because that should be in your LA worksheets. Make early assumptions and dive deep into those assumptions. And then always look at REX for what the value is returned from. What value is returned from the call queue. Understand like test queue, compare queue, what they do. Test queue ands the 2 registers together. Understand like the dynamics of if you add 2 things together, it will only become 0 if the register itself is 0, right? That makes sense. Okay, that's the fundamentals for that question. This one I would say is one of more of a harder conceptual question, because you have to draw the stack. Just like I would suggest doing a couple of these problems. Like understanding conceptually, like this thing is really important, but that's not enough. What you need to do is actually track each instruction and see how it manipulates the stack. And you should do that by going line by line and drawing the stack and keeping track of your registers. Okay? One thing is important is the push and the pop and the call queue and the leave queue. If you understand like the 2 things that each of these instructions do, or like not even understand, just write on your cheat sheet and just do that thing exactly, over time you'll just get a lot of more intuition, right? If you just rigorously understand what each instruction does, there should be nothing really stopping you that much. Of course, there's still like random BS in the bomb lab, but you just gotta thug it. So I hope all this helps. Thank you.